last paper of the AGT Fest is Welfare Guarantees from Data. This is a paper by Darrell, Denis, Nekipelov, and Vasilis, Syrgkanis. I don't want to steal Vasilis' thunder, so I just want to say that one of the things that the committee was really struck by this paper was what an elegant marriage it made between canonical questions in econometrics and how you look at making estimations from the data we gather, and a topic of the question in AGT, meaning the price hierarchy, which has one of the longest traditions in AGT. And so this paper is something we hope we see a lot more of, this kind of branching out and bringing AGT into econometrics. And so let's see this.
Thank you very much, Jason. Thank you very much for inviting me. It's a great honor to present at this session. So let me just start. Jason made a very good introduction to the paper. So one of the questions that we have well studied in the algorithmic game theory field is when you have a non-truthful auction with one or more items, how well are goods allocated? So how approximately optimally are they allocated? In particular, can we compare the expected equilibrium welfare that we will get under some notion of equilibrium or under some notion of strategic behavior, let's know that with EW, to the optimal welfare that we could have attained had there not been incentives and we could allocate, we knew the values that the players have for all of the items, that we could allocate the items optimally, so solving just the algorithmic problem. Another way of viewing this, so one way of viewing this is what is the impact of incentives on efficiency, or what is the loss from not switching to a VCG auction, which is a computationally non-efficient auction. In this work, we basically contrast, we started by contrasting the two approaches that you could take at addressing this problem. From the theoretical computer science literature, what we have mostly done is try to prove worst case bound on the price of anarchy ratio. And excuse me for the price of anarchy people, I'm going to use in this talk the inverse of the price of anarchy as the ratio, as I want to basically be talking about welfare guarantees. So what I'm going to be talking is what fraction of the optimal welfare is achieved at the equilibrium. Okay. And so there's a big line of work trying to prove such worst case bound, worst case over the valuation distributions and the equilibria that could have taken place in the auction, and sort of lower bounding this ratio in the worst case. Many times this ratio is bounded by some non-trivial constant, and that was considered a success. On the other hand, you have econometrics, where in econometrics, the way that you would address this problem is that you would assume that you observe some bid data set from the auction that you're deploying. And then based on this bidding data set, and assuming some notion of equilibrium, you can sort of try to infer what is the underlying value distribution that the players have for the items as a function of the observed bid distribution. And then based on the data, you can sort of estimate or approximate this underlying value distribution. Once you have the underlying value distribution, you can sort of go and calculate the quantity of interest that you want to estimate, which, for example, could be the ratio of the expected welfare at the current equilibrium as compared to the optimal welfare. And so there's also a lot of work in econometrics on understanding the structural econometrics of auction settings and non-truthful auctions. For example, there is a very famous paper by Perrin and Wong that analyze this inversion going from bids to values in the setting of a first price auction. And there's also a lot of work in addressing ad auction settings like the generalized second price auction. Now, the two approaches have some benefits and drawbacks. So the theoretical worst case price of anarchy approach is in some sense robust. You don't depend on some data collection process. You don't make a lot of assumptions about what equilibrium is selected or what equilibrium is being played. You don't have any sampling errors or finite sample errors. But on the other hand, it's very pessimistic in the sense that it tries to quantify this ratio in the worst case over all possible equilibria and over all possible value distributions that could have arisen. And many of these value distributions that would achieve this lower bound might be unreasonable to expect in practice. On the other hand, the econometrics approach is more data-driven, so it leverages the data to sort of understand the average case quality over the instance-based quality of your auction setting for the particular setting that it's been deployed. But on the other hand, it's very fragile in that it requires some specific notion of equilibrium most of the times, and the sampling errors are typically depend on non-parametric estimation approaches, which are terrible in finite samples. Okay. So this work is trying to bridge across these two approaches and to use methodologies that have been developed in the price of anarchy literature but replace worst case analysis in those methodologies with the existence of a data set. So suppose that you have a data set, how can you alter the proofs, these worst case proofs, in a way that adapt to the particular setting you have at hand? So let me just give you the idea behind this work through a very simple example. Going also like Ben also made a nice introduction. I'm going to focus on the first price auction, which is one of the most well-studied auctions. And I'm going to look at, for now, for the purpose of the talk, I'm going to look at this, the Bayes-Nash equilibrium of at the Bayesian sort of like formulation of a first price auction, where each player has some value vi, which is drawn from a commonly known distribution fi. And we're going to assume that the bidders in this auction are going to play according to a Bayes-Nash equilibrium, which means that their bid is going to be, for conditional on their value, their bid is going to be a best response to the distribution of opponent bids. So let GI denote the CDF of this maximum bid except player I, of this maximum other bid. Then a player in this auction is going to assume that is going to believe that he's getting an expected utility from any bid BI that is equal to his value minus his bid multiplied by the probability of winning, which is exactly equal to the CDF evaluated at that bid BI. So I'm going to go through how in the worst case, in theory, we can analyze a lower bound on the price of anarchy of a first price auction. And then I'm going to show you at which point in the proof we can sort of go and say, now that we have data, we can have a more refined analysis of the price of anarchy. So how would a standard price of anarchy proof go in a first price auction? Well, it will go through some deviation argument, similar to how Ben, for example, used deviation arguments to bound the revenue guarantee. You can also use deviation arguments to bound the welfare guarantee. The standard sort of deviation in a first price auction that has been used in many papers is, for example, suppose that the player, instead of bidding his current equilibrium bid, he's deviating to this randomized bid, where with probability 1 over this, like sort of like the utility from that bid, 1 over vi minus bi, he's deviating to bid bi prime. And so this is the density, and such a density must have support in 0 and 1 minus 1 over e times vi. Now, pictorially in this picture, I'm showing the CDF of the maximum other bid. This is the value of the player, and this is an arbitrary deviating, and this is his, let's say, his current bid at equilibrium. And so you can see that this rectangle is equal to his expected utility at equilibrium, because it's his value minus his bid multiplied by the probability of winning. Now, the utility of such a deviating bid, you can easily also see it pictorially. If he deviates to some bi prime, then this other rectangle is his utility from that deviation, and because he plays it with this much density, you need to divide by one side of the rectangle, so you're going to get this slice, and then integrating, you're basically going to get this area under this curve. Okay? So the deviating utility from such a deviating bid is equal to the area under this curve from 0 to 1 minus 1 over e vi, and now the proof goes this utility plus the area above the curve, which happens to be equal to the expected maximum other bid, because it's the integral of 1 minus the density, and that's just a standard fact. So this deviating utility plus this integral above the CDF has to be at least equal to this rectangle, which is equal to 1 minus 1 over e times the value. So you have this inequality. Now you can multiply this by any allocation function that you want, and say xi now is the optimal expected allocation of a player in the optimal allocation. If you also have the fact that the revenue of the auction is at least this quantity over here when you sum it across players, which is true because the revenue is at least the maximum bid, and so it's at least this convex combination of maximum other bids, then you can rewrite this inequality by saying the total utility at equilibrium plus the revenue at equilibrium is at least 1 minus 1 over E of the optimal. And revenue plus utility by quasi-linearity is equal to expected welfare. And so you get that the expected welfare at equilibrium is 1 minus 1 over E of the optimal. Okay. So the main fact that we used in this proof was that one of the key steps that we used is right here when we said that the revenue at the equilibrium of the player is at least the summation of these quantities Ti. Okay, so these are the revenue is at least the maximum other bid, or it's at least some threshold for winning, some expected threshold for winning. And there is a generalization of this theorem presented by Jason and by Hardline et al. In their work that says that if you have an inequality that says that mu times your revenue is at least this threshold quantity, then you can get a price of anarchy bound. And this mu is also reminiscent of like the lambda mu in the lambda mu smoothness framework, and this is sort of a more refined and a more intuitive reformulation of smoothness for the case of auction settings. And the previous proof basically showed that the first price auction is one revenue covered. If you could show that your auction is mu revenue covered for some other values of mu, you can see that you get some sort of like nice interpolation of the price of anarchy from 1 up to 0. And so the main idea in this work is that if you have bidding data, then you can actually go and measure this quantity mu from your data. Okay? So this mu, you don't need to take a worst case, you don't need to make a worst case proof about it. You can just measure it from your data set. Okay? And why is that? Like if we knew the population, say in a first price auction, you knew the population distribution of bids, then the expected maximum other bid is identified, uniquely identified from the data. The revenue is also uniquely identified from the data, and so you can just calculate this ratio and not use a worst case bound on it. Okay. And in fact, if you have samples from the data rather than this limit population distributions, you can also estimate these quantities at a very fast rate, because these are just estimating a CDF, and so you can estimate it at root n rates, so parametric, almost parametric rates. And this is in contrast to the approach that you would have typically taken in econometrics that requires estimating densities of distributions, which is much slower than estimating CDFs. Okay. And so this is the main idea. This idea extends also beyond the first price auction to any single-dimensional mechanism design environment. In such environments, you have to appropriately extend this quantity, what this quantity Ti is. It's not the expected maximum other bid, but it's an appropriately defined quantity. And we also saw in this work that this generalized quantity can also be estimated from data at order tilde root n rates for many auction formats that are used in practice, like the generalized second price auction. Another thing that this approach inherits is for the robustness of the price of anarchy literature, in that like the guarantee that we're going to get by just measuring this mu from the data and not doing any more econometrics is that this guarantee is also going to extend even if the bid distribution was not coming from a Bayes-Nash equilibrium, but was coming from some sort of other more game theoretic solution concept like no regret learning or correlated equilibrium or Bayes correlated equilibrium, etc. And it also degrades gracefully if you assume that the bids are an epsilon equilibrium and not an exact equilibrium. Typically, all of the previous econometrics assume an exact equilibrium and heavily rely on a bid inversion that is very brittle to not an exact equilibrium. Okay? So this is the main result of the paper. We also went and applied this in practice. So we went to data sets from Bing Ads, and this is a multi-billion-dollar industry, and we try to analyze what is the empirical price of anarchy, in some sense, of the generalized second price auction for several popular keywords in the Bing Ads system. And here, for example, I'm giving you this fraction that we recovered for many of these popular keywords. And the main thing to observe is that the generalized second price auction, it's not even a revenue covered in the worst case. Despite this fact, the empirical price of anarchy can still be lower bounded by some trivial guarantee. So formally speaking, the generalized second price auction, there is no worst case sort of like revenue covering proof. If you want a worst case proof, you have to typically assume some no overbidding assumption. But when you go to the empirical price of anarchy, you don't even need to make such assumptions. And by leveraging the data set, you can typically get higher welfare than the worst case welfare guarantee. You can get up to 70%, while the worst case is approximately 30%. So that's it. So we propose an empirical version of the price of anarchy analysis, which blends the theoretical and the econometric approach. This combines the robustness of the worst case guarantees and the extra information that we can get from data sets. And it's applicable to any single dimensional auction setting. And we gave an example application of it to Bing ads. And that's, thank you. Why is the oh, so yeah, so it's in the click-through rate curve heavily affects this threshold for winning. How much competition is there also affects the threshold for winning. And so it's this, how does the threshold for winning curve looks like is what affects this worst case guarantee.